For number 10, we're constructing a confidence interval, a 95% confidence interval about the difference between two means. Now, here we have independent samples. There's no mention of them being paired up, and we can also tell that we don't have matched paired data because the size of each sample is different between our experimental group and our control group. So we will want to go into StatCrunch here, and we can look at stat and then our t-stats. We have two samples, and we have the summary data listed. So our sample 1 had a mean of 47.5. And then go ahead and enter in the rest of the information for each of your samples. And then you'll want to make sure you've clicked confidence interval and the correct confidence level. And when you hit compute, you'll get the lower and upper limit of your confidence interval for the difference between the two means. For number 11, we're doing another comparison of two means, and it tells us what we're testing here. So that's going to be our alternative hypothesis, and our null hypothesis is always that the two means are equal. Clicking here for viewing our data, there's no mention of them being paired in any way, and we can see that there's different sizes in each of the two samples, so we know it's not matched paired data. And once again, we can go into StatCrunch and enter in these summary statistics. We want to go to stat, t-stats, two samples, and we have the summary statistics. So enter in the information for mean, standard deviation, and sample size for each of the samples. We're doing a hypothesis test this time. Our null is the equality. There's no difference, so the subtraction is equal to 0. And our alternative was the less than. And when we go down and hit compute, we'll get our p-value for our comparison of the two samples. And 0.001, that's less than our significance level of 0.02. Anytime our p-value is less than alpha, we reject the null hypothesis. The low p-value like that gives us sufficient evidence to conclude that our alternative hypothesis is correct. For number 12, we're looking at the situation where we're comparing the speed people walk when they are getting off a plane compared to when they're getting on a plane. And we just want to know if there's any difference in how fast people are walking in those two situations. And so we're going to test that with a hypothesis test. Our null hypothesis, like always, is equality, that there's no difference, that mean speed people walk is the same in both of those situations. And because we're just looking to see if there's a difference, our alternative would be that not equal to see if there is a difference between those two means. And so I started there with C, just talking about what our null and our alternative would be. And so to go back to A and B, why is this an observational study? It's because the way it's being conducted, someone's just sitting in the airport and watching people. So that's a classic example of a good observational study because the data is not being influenced at all. Someone's just observing what is happening. And as far as Welch's t-test, we have random samples here, just random people in the airport. They're large samples and they're independent. One person's walking speed is not going to affect the next person. So, and you can see our data here. Our sample sizes are 35 here. They're both large enough. And so we're going to go into StatCrunch and use this summary data to conduct our hypothesis test. And so enter in all that summary data, and you'll want to make sure hypothesis test is checked and that we have the not equals to as our alternative. When we hit compute, we get our p-value for testing the difference between the means. And like always, if our p-value is larger than alpha, we do not reject the null. And in this case, 0.609 is quite a bit larger than 0.1, so we do not reject the null, which means we can't assume the alternative is true. There's no reason for us to believe there's a difference in how fast people are walking compared to when they are arriving or when they depart from an airport. And number 13, we're again comparing two populations. And our first one is adults with no children under the age of 18, and our second one is adults with children under the age of 18. And we're comparing their average amount of leisure time. So all the information from our two samples is listed in the paragraph. We're going to go ahead and put that into StatCrunch. So in StatCrunch, we want to go to Stat, T Stats. We have two samples. We have the summary data. So we're going to enter all that in. And right away, we can see there is looking like there's quite a significant difference for the mean amount of leisure time. Our people with children look like it's quite a bit less than the people without children. The numbers are just smaller here. So to create the confidence interval, let's make sure we get the proper size. We wanted a 90% confidence interval. So make sure we change that to 90 and then hit compute. It'll give us the upper and lower limit of our 90% confidence interval. And so we're 90% confident that the difference of the means is within this interval. And since both these values, the lower and upper limit, are both positive, it means that 0 is not in this interval. And so we're 90% confident that the difference of the means is not 0, because 0 is not one of the options in this range. And so that gives us reason to believe that there is a significant difference between the population means. And number 14, a professor is teaching the same exact class in two different ways. Well, everything's the same except for the homework. And so the first way, he's doing online homework, and in the second way, it's traditional paper pencil homework, and just trying to see if there's a difference in the outcomes on the final exam scores between those two different methods. And so first we want to determine what type of experimental design this is. If you go to question help me solve this, it breaks down our different options for experimental design. It's a good place to find a refresher on that. So you could read through those to see why this is a completely randomized design. Our response variable is what we're hoping to try to measure if there's a difference in by doing our experiment here, and we're looking at the final exam scores. And our treatment then is what are we changing along the way to try to measure if that change has any effect on the response variable. And what we change here is the homework system. One time it's online homework and the other time it's traditional paper pencil. And again, in question help, you can get a nice refresher on what response variables are, treatments, and the next one we're talking about, which is controlled factors. And that's the factors that are intentionally kept the same in order to ensure that those factors aren't having an effect on our response variable, our outcomes in this case, that they aren't affecting the final exam score. And so in C, we're trying to list all the factors that are controlled in the experiment. And you can read up here in the paragraph the things that the teacher intentionally is keeping the same from one class to the next. And so those are all checked here. Some things can't be kept the same, like the weather. So that's not something that would be a controlled factor. In part D, it's talking about why is this random, because we definitely want both of our samples to be random. And in this case, 2 courses with students enrolling in them, that's pretty much a random process. Students aren't chosen for the course. It's just the luck of the draw who enrolls at any given time as to determine what the makeup of each of the 2 classes is. And then so finally, we want to conduct our hypothesis test to actually see if there is a difference in our final exam score. So our null hypothesis is always equality, that the 2 means are going to be the same. And we're trying to see if the homework system, the online homework system that was used in the fall, has better scores than traditional paper pencil. So that's why our alternative is that our fall class, the one that used the online homework, is greater than the spring class. So if we look at our table of data, we're going to want to enter that summary data into StatCrunch. And so copy all that data in. We're running a hypothesis test. And what we're testing for is greater than for the difference of the means. So when we hit compute, we get our p-value. And if our p-value comes back, which in this case it does, larger than alpha, which our significance level is 0.05, whenever it's larger than that, we cannot reject the null hypothesis, which in this case means there's not sufficient evidence to conclude that classes in general using the online homework like our fall class did will score higher on the final exam than classes using traditional pencil and paper homework like our spring class did.